All right. Good morning, everyone. Happy Friday. So today we're going to first, finish talking about galaxy bias. So last time we introduced the galaxy bias expansion that should be on the slide, but it's not working yet. Okay. Well, anyway, the idea is that we want to write down the most generic expression for a function that describes how galaxies depend on the underlying dark matter field. And we're using symmetries. So, okay, it's an unknown function. We're using only symmetries and dimension analysis. So we discussed that the very simple, the simplest possible function you could write down is going to be just a linear function. And then there could be corrections to it. And then by symmetries, it's not enough to write down just delta squared. You also would want to write down something like the tidal field, etc. Okay. And we discussed that at the cubic orders, there will be a few terms whose general structure will look like this. Delta cube, right? And these terms will produce contributions that are 100% degenerate with the linear bias term. In particular, so P13 delta cube delta will be simply B3 times the mass variance times P11 of K. And we discussed that this leads to an unobservable renormalization of linear bias parameters. Oh, excellent. Okay. So in particular, the total functional form produced by this correction will look like this. P11. So you just say that this is B1 renormalized squared times P11 of K. And this is the reason why we can totally ignore these terms at the level of the one loop galaxy power spectrum. Okay. Another important effect that we started discussing last time is the presence of stochasticity. So we know in general that the galaxy distribution is not 100% correlated with the underlying dark matter field. There will be some corrections produced by the completely virialized modes. So we discussed these corrections in the context of the dark matter field, but also you'll have the same effect in the context of the galaxy bias. So in other words, when you write down this function, you start with the linear term, but before writing the linear function, there is an even simpler function, which is a constant, right? So this is your constant. (5.3) stochasticity. And the appearance of this constant actually, so I'm going to write down this like that. Delta galaxy total is going to be delta galaxy deterministic. So this I'm going to call deterministic, right? So it's a function of delta. It's deterministic that for given cosmological initial conditions, you can calculate the galaxy density field completely within this picture, right? But on top of that, there will be some error in this description that is produced by the stochastic fields. And the presence of the stochastic fields is actually very deeply connected to the UV limits of these contributions. So in particular, so we discussed last time that if you want to compute the, P galaxy one loop, what we need to do is that we need to, insert the perturbative expansion for the nonlinear density field of matter as a function of the linear field, and then, Taylor expand everything, and it will produce a bunch of terms. So once we have expansion, we just compute the usual P2, P13 diagrams. We're going to get a bunch of terms. And some of them, like in particular this I delta squared, which is the auto spectrum of the delta square field. So write down like this. We'll have some interesting properties that we haven't seen before. Okay, so this expression, so we can easily compute this. The B2 term there, well, you can see that its kernel is trivial, right? Its kernel is just 1. So its corresponding P22 contribution will take a particularly simple form. It will be just P of Q times P11 of K minus Q, okay? So before we used to have F2 squared, but F2 squared here is 1, so this term is very simple. Okay, so now we can take a UV limit of this expression, UV limit, which as before just corresponds to formal limit, let's say K going to 0. Now this term that I called there I delta squared, okay, we can recover the coefficients, B2 squared over 4. Okay, so when K goes to 0, this is the only term that modifies, so instead of K minus Q, just get P of Q, right? So you're going to end up with the expression that simply looks like this. So 1,4 is taken out as a definition. So it's just going to be the integral. I'm going to write down the measure very explicitly. P11 of Q squared. And in this limit, formally, okay, we start from some IR cutoff. Let's for simplicity put this to 0, and then it goes to some UV contribution. So you can see that this correction is constant, right? It doesn't have any K dependence. And again, we need to renormalize it. And if you just naively look at all these expressions, you don't see any constants, right? So this is how, well, in some sense, how to see the necessity for the stochastic fields from the point of view of renormalization, right? You need to introduce some other fields whose correlation is constant in order to absorb the UV dependence of this term. So we have this epsilon field, and as we discussed last time, well, here, maybe I should say that this epsilon is different from the epsilon of dark matter. Maybe we can write down epsilon of galaxies. So epsilon of galaxies is uncorrelated with the cosmological initial conditions, but tends correlate with itself. And again, we can use our standard arguments, symmetries and dimensional analysis to say that it should start, so its two-point function should start with some constant, and then in a limit of very large scales, and then the correction to it will scale like K squared, and there will be a Taylor expansion. That's the only thing you can write down. And now you can see that this constant, alpha naught, will precisely renormalize this integral. So let me write this down schematically. I delta squared, B2 squared plus alpha naught. So this will give me, again, so there will be a part of this integral that is calculable, that makes sense to keep, that doesn't have a big mistake. The integral going from 0 to k nonlinear. And then there will be a piece going from k nonlinear to lambda, which needs to be normalized. And precisely here we can say that our alpha has an infinite part, lambda dependent part, that exactly cancels this, and then has some finite part. Okay. And you can check that with the rest of these terms, you can totally renormalize this expression. So basically, with this contribution, most of the deterministic terms are going to be renormalized either by bias parameters themselves or by this higher derivative bias that kind of plays a role of the sound speed. So it renormalizes all the k squared times p linear contributions, and then all the constant contributions will be, so all the contributions that do not depend on the linear matter power spectrum will be renormalized by the shot noise. Even from this expression, you can already see, so you can ask the question, okay, we Taylor expanded here at the zeroth order, but what would be if we kept, including corrections for small but not 0k. So the first correction that will pop up at next to linear order will be k squared times a constant. And this will be exactly renormalized by alpha 1 tilde. Okay, now physically, so after you have renormalized everything and stuff, so physically, you can ask the question, okay, what does this mean? You know, the residual part, alpha not finite, what's the physical meaning of that? And the physical meaning of that will be related to the galaxy shot noise. So we know that. Okay, so how to estimate alpha null, alpha not tilde, etc. Okay. So if we have a random collection of particles, we can compute the overdensity field. So we have n, let me use capital N random particles. I'm just spreading n random particles, so you can easily calculate, take the Fourier transform of this expression, that the corresponding power spectrum will scale like V over n, which is 1 over n bar. That appears also here as a background density. So if you have a bunch of random particles, they will have a power spectrum on large scales, which is constant, proportional, and it will be proportional to the inverse of the number density. And this is physically what alpha naught finite describes. So obviously, a random distribution is uncorrelated with the cosmological initial condition. So this is precisely the power spectrum of the stochastic field. Now, from the EFT point of view, you know, in this simple picture, the power spectrum on large scale should be exactly given by 1 over n bar. But in the EFT picture, there should be always some sort of finite, well, order 1 parameter. Now I'm going to call alpha naught without any tilde. Now alpha naught is dimensionless. It's an order 1 parameter. And we know that there are physical effects due to which, even if you start from a random distribution of particles, still you are not going to recover this 1 over n bar term. It will be slightly higher or smaller because of the so-called effect of the halo and galaxy exclusion. So in other words, of course, if we talk about random particles, this is fine. They can take any position, but for the realistic halos, if you already have a halo, you cannot place a different halo inside it, right? So there is some sort of correlation that will be additional correlation will be produced simply by the fact that you cannot put two halos in the same point of space, right? You cannot put them completely at random. And this typically leads to alpha naught not being 1. So alpha naught will be, well, typically is like on the order of 0.1, point few, something. And then this depends on whether you're looking at the very massive galaxies that occupy a lot of space or tiny galaxies. That is to say that it has the value of alpha naught carries this information about the exclusion of galaxies and halos. Okay. And probably the last comment that I would like to make here is that here you see the appearance of a new scale. So very roughly from this expression, if we want to estimate the power counting, all these bias parameters are order 1 functions, so order 1 coefficients. For instance, B1 for red luminous galaxies is about 2, for emissional galaxies 1.5. So they will not change the usual scaling in a sense of the separate universe. So imagine when I estimate these things, we can still use the separate universe argument. They just introduce order 1 coefficients, so they will not change our counting. When it's the counter term, again, or the k-squared term will be as important as all the one loop stuff. But this 1 over n bar will introduce a new scale. And in principle, this is something that selection specific. And in particular for, well, as Elizabeth described in her class, current galaxy surveys, such as BOSS and DAISY, they operate in the regime where P11 of, let's say, k around 0.1, h over megaparsec times n bar is of the order of few, right? Yeah. That's right. Yeah. Once you subtract the divergence, so the b2 squared, piece will be here. It's a calculable part of the loop that you need to keep, and then you will have some finite contribution. So you'll absolutely, yeah, absolutely, yeah. Yeah, absolutely. Yeah, 100%. Yeah. So it introduces truly a new scale. So it's a scale of the expansion of the stochastic field, right? Which is different in principle from the scale of the expansion of this. Okay, so, well, anyway, from this argument, you can see that these terms, well, typically are, well, basically the stochastic terms, 1 over n bar, they scale more or less same way as the tree level contributions. And the k square correction then will scale like one loop. Oh, right. Oh yeah, absolutely. Yeah, you could. Well, actually, this is exactly the next topic that I was going to cover. This renormalized. Yeah, you can totally do that. You can go to the operator basis that is renormalized, right? And then in that case, um, well, this will secretly still include this contribution, right? Because this will appear when you renormalize. You need to write down, like your normalized local operators. You need to write down all possible counterterms. You need to write down this as a counterterm again, right? But this way, maybe you will see in a more clean way that this part will be cancelled, and then there will be like a finite piece. Okay. But yeah, this is completely true. Okay. All right. So I think that this will be it with the bias tracers. Let me see if there are questions. Okay. If not, let's move on to our last topic, which is space distortions. Okay. So the origin of ratio space distortions lies in the procedure that we use to map the galaxies from the sky onto the Cartesian box. So basically, when we see a galaxy, okay, we see it on the sky. It has two sky angles and redshift. So spectroscopic galaxy has a well-defined redshift. And in order to compare this with our theoretical predictions, which are formulated in three-dimensional space, okay, we would want to map this onto a box. Well, we know that we can always relate angles to the angular diameter distance. So we can always use those to reconstruct two coordinates. But then if you were to interpret the redshift of your galaxy naively as a line of sight position, you're going to generate some bias, some distortions in your observed galaxy maps. And this is because the redshift that you observe, it's true that it depends on the actual physical distance via the Hubble law, but then on top of that, there will be a contribution from the peculiar velocity and you don't know for a given galaxy what its peculiar velocity is. Right? So in this way of inference of distance using redshift, you're actually recovering something that's called the something that is called a redshift space coordinate that I'm going to call S. And now we can go to the co-moving redshift space coordinates. So we divide it by A and H. Also now I'm going to recover the full three-dimensional vector this way. So we have R physical over A plus VZ. So we'll have this extra contribution only along the line of sight. And here you can see from this expression that our redshift space, co-moving redshift space coordinate will be the usual co-moving coordinate plus this contribution, where again you can see the appearance of the conformal Hubble parameter, times the Z projection of the velocity field of the galaxy onto the line of sight. And the Z here is the unit line of sight vector, which normally we define as 0, 0, 1. Okay. Now, what does this mean for us? For us, this means that the galaxy distribution that we reconstruct using the redshift space coordinate will be transformation, well, a distorted map of the actual galaxies, where every single galaxy will be shifted by its velocity. So hence the name redshift space distortions. And we know that V, again, is a cosmological random stochastic field. So this field has some cosmological correlations. We know for linear theory that it's going to be, V just the gradient of the density field times 1 over Laplacian. So this will introduce, as you can see from this expression, this will introduce additional dependence on the deterministic cosmological fields. And in order to account for this dependence, okay. This is called redshift space mapping. Okay, in order to account for this dependence, the simplest way is to notice that in redshift space, when you move from real space to redshift space, you don't change the number density, you don't change the number of galaxies, right? So the total number of galaxies is conserved. You don't generate new galaxies. So you can use this now to relate, you can use basically the tracer conservation to relate the density field in real space and redshift space. Well, another way to account for this effect is to notice that this is simply a coordinate transformation from the galaxy frame to the observer frame, right? And now you know that the density is part of the T mu, and you can account for it just by using the usual equations of GR. And this is your transformation. So we know how we do T mu dx 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 dx, right? So schematically. So this is another way how you can arrive at this. But it's it's more clean if we use this tracer conservation story. So the conservation of galaxies implies that their total density, so background density times the perturbation, their total density in redshift space and the real space will be the same. Well, here this is the density, this is the volume. So now you can see like the total mass, well, total number of the galaxies, right? The total number of the galaxies conserved, and from this equation follows. So now we can go into Fourier space and just rewrite this into Fourier space, and then there will be a nice simplification that will come from the fact that we could use a Jacobian. You know, we can basically divide d3x over d3s, and then uses a Jacobian to change coordinates in the Fourier transformation. So in other words, after some simple linear algebra, well, in this case, just not even linear algebra, some simple algebra and games with the integrals, we're going to arrive at an expression that will look like this: to the minus ikx minus ikz vz of x over curly h minus 1 times 1 plus delta galaxies of x. All right. So now you can see this maybe more clearly, that the overdensity field of the galaxies, so overdensity of galaxies in retro space will be given by overdensity of galaxies in real space plus some transformation term that basically looks like a Fourier transform, but in addition to the usual ikx in the Fourier transform, it has the piece that comes from the retro space mapping. Now, to simplify notations, let's introduce a rescaled velocity field that I'm going to call U, which is the usual V divided by F and curly H. So we know that in linear theory, this will be just minus gradient delta 1 over Laplacian. So now with this notation, we can streamline some of the expressions, and in particular for the retro space mapping, we're going to get the expression that looks like this. Okay. Let's now see what are the predictions for the clustering of galaxies in retro space. And the first prediction is the linear theory prediction that is described by the so-called Kaiser formula. All right. So the idea is that in linear theory, we can Taylor expand this exponent, this part of the exponent that depends on the velocity field. And in that case, well, here you have minus 1, so we'll have the velocity field sitting here. And at linear order, we can ignore the galaxy field in these brackets. So we're going to find the usual overdensity field of galaxies in real space plus d3x e to the minus ikx minus if kz uz of x. Now, as I wrote above, uz of x is minus dz delta 1 over Nabla squared, and we have a nice Fourier transform that will allow us to rewrite this Laplacians in just 1 over k. So altogether, here at linear order, we can use the linear theory prediction b1 times delta 1 of k. And what we get here is, once we have done the Fourier transform, will be f kz squared over k squared delta 1 of k. So we have one kz here, the other kz here, divided by the k squared. Hence this, and f just comes, well, basically f comes from the relationship between the velocity and the density field. So in other words, we're going to get an expression that looks very similar to the usual linear bias, but then it has an extra dependence on on the wave vector. So now we can see from this expression that the clustering along the line of sight, right, where kz is non-zero, the clustering along the line of sight is enhanced. And the amount of enhancement is precisely proportional to the logarithmic growth factor. So this enhancement is known as the Kaiser effect. Well, we can formalize this and well, compute this enhancement at the level of the galaxy power spectrum ratio space. We're going to find the expression that will look like this: P1 plus F mu squared P11 of K, where mu is Kz over K. All right. So this is the famous Kaiser formula. And the physics that it describes is very simple. So the idea is that, so if we, okay, imagine that we have an actual picture of galaxies that are moving together in one big flow, kind of attracted to each other by gravity. So they're moving towards each other. They have velocities, directed at each other. In that case, the apparent picture that we will see by assigning the coordinates of these galaxies based on their redshift will be like this, right? So the galaxies will appear in our redshift space. They will appear closer to each other, right? So hence their clustering will be enhanced, right? Because this looks as if you have a collection of galaxies that are more clustered than in this case. So this is the idea of the Kaiser effect. And you can see that again, this is only effect for the line of sight modes when mu equals 0. So if you have Fourier modes that are completely lined in the sky plane, so they're perpendicular to a line of sight, in that case, nothing ever happens, and the expression will be similar to the usual expression for the galaxy power spectrum in real space. Okay. All right. At this point, maybe let me mention that so Kaiser formula is the linear formula. But when people first started dealing with the redshift space distortions, sorry, let me use this blackboard. So when people first started looking at redshift space maps, they noticed another effect that was very pronounced. That was called fingers of God. So now, yeah, let's play again this hypothetical game. So let's look at two galaxies that are sitting in a halo, right? So two galaxies that are completely virialized, they're sitting in a halo or a galaxy cluster. So they have virial velocities. Virial velocities, as we know, are large. So now imagine that, okay, you have these big virial velocities. So now these galaxies, they will have big projections on their velocities along the line of sight, right? So that means that, so this is the actual picture. Now, if we were to map the distribution of these galaxies based on their redshifts, what we're going to see, well, basically what we're going to see is that this galaxy will be here and this galaxy will be here, right? So we're going to see them like that. And now you can imagine if we have more galaxies sitting here, we're going to find some distribution. So the galaxies in a cluster will naturally align themselves along the line of sight. And this is what is called fingers of God. Well, people started seeing these features in galaxy surveys in the 70s. And first, of course, they were very surprised, but then they realized this is exactly because of this effect. Now, unlike the Kaiser effect, the Kaiser formula, you can see that fingers of God are fully non-perturbative effect because it has to do with the virial motions, okay? So this is something that we're going to understand today how to describe in perturbation theory. But this effect is very important, and in the literature you will see a lot of discussions about fingers of God. Okay, are there any questions maybe at this point? Yes, please. Yeah, so what happens in the EFT is that the shell crossing is captured by the stress tensor, the shell crossing in dark matter. Well, basically the idea is that we're going to use the large scale coarse grain velocity field that doesn't undergo shell crossing. And then the effects of shell crossing are incorporated by the stress tensor effectively, right? So in this description in the EFT, kind of the velocity field, okay, the velocity field as everything in the EFT is, well, you need to worry about renormalization, cutoff, and things like that. But let's say the lean order picture is that this field is specifically a large scale long wavelet part of the velocity field that never undergoes shell crossing, so it's always well defined, so we can use this formula. Okay, good. All right, let's get back to our Kaiser formula. So you can see that the dependence on the line of sight variable mu. So mu simply is a cosine of the angle between k and z. So its dependence at linear order is simply polynomial. So we have the part that doesn't depend on mu, part that depends on mu squared, and part that depends on mu to the 4. So historically, people, they derive the linear theory prediction, and from this expression, it seems that, if we have only a few functional forms, well, here only 2 possible powers, we can just recast this equivalently in terms of the Legendre polynomials, and we'll have to keep track only on 3 Legendre polynomials here, right? So we know that the Legendre polynomial of the 0 kind is 1, the Legendre polynomial of the first kind, of the second kind is 3 mu squared minus 1 over 2, and then the expression for the fourth order Legendre polynomial is a little more complicated, but also well known. Okay, so using these expressions, now we can reshuffle our expression for the ratio space galaxy power spectrum and express it in terms of the polynomials, Legendre polynomials that depend on mu. And this is something, okay, there is a very easy, very simple way to extract these things. It's just a simple linear transformation or a rotation of the basis in a mu space, if you will. So we will end up with these expressions. That now you can rewrite as P naught of k times L naught of mu plus P2 of k times L naught L2 of mu times P4 of k times L4 of mu. Okay, so what's nice about this is that now we have completely factorized k dependence. Depends on the wave number and it depends on the wave number's projection on the line of sight. We factorize into k mu like this. For each Legendre polynomial, there is just a simple function of p of k and mu. And in linear theory, they will all be proportional to p11 of k. It will get multiplied by some. Constants. Okay, so this is something that is known as the multiple expansion of the galaxy power spectrum. So these functions that appear here are the power spectrum multiples. All right. Now, very good. How to go in this picture? How to go beyond linear theory? Okay, this is really easy. We just have to take this expression above and Taylor expand, okay? And keep terms that are nonlinear in delta. So this way, we can again, well, go through the exact same procedure as we have done before. So we Taylor expand, and this way we're going to get an expression that will look like this. So the square brackets, they represent Fourier transforms. So basically, this is exactly the expression that appears here is 1 plus delta galaxy in real space times uz, and then we need to take a Fourier transform of this, right? So this expression is already in the K space. All right, this is just a simple Taylor expansion. So now, again, we can play the same game as before. We know that the galaxy, so the galaxy density field is a Taylor series in the initial density field. We know all its kernels, you know, K1, K2, K3. Now we also have the velocity field. For the velocity field, we also know that in linear theory, it's just going to only be given by the, well, it only depends on the longitudinal part, right? So, well, basically, this is going to be your gradient of theta that I introduced before. And we know that theta also has an expansion in terms of delta naught and the nonlinear kernels G. So now we plug all these things together, and we're going to arrive at the expression that will look like this. So schematically, again, there will be just bunch of integrals with the nonlinear kernels, and the structure of these nonlinear kernels will just be given by the combination of the bias expansion and the standard perturbation theory expansion. So in these kernels, I have written down, oops, let's see. Yeah, so you can see them here. Okay, this is galaxy kernel, sorry about that. Yeah, okay. Oh. So it's not responding to my slides. Maybe now it will. Okay, maybe now it does. So the thing is, when I'm going to the full screen mode, then it says my screen sharing is paused. But okay, it's not a big deal. Oh, it's okay. Well, anyway, now you can appreciate the structure of these kernels. Well, you can see that the linear kernel is just the usual Kaiser term, and then the quadratic kernel has a lot of the terms just from the linear bias, right? Sorry, from the quadratic bias, so it has usual quadratic bias. These guys do not get modified. And then you have the additional terms that come from the, well, basically from here, right? So you have some sort of pure velocity term at quadratic order, or you ignore this, and this you expand to quadratic order, and then you have a mixed term where the velocity field is linear and the density field is linear, so you get some sort of modified Kaiser expression. And then at cubic order, the expression is more complicated, but again, the idea is just you just really kind of evaluate all these things in perturbation theory, okay? You can do it with Mathematica, it takes very little time. Okay, so this is all good. Now you can ask the question, okay, what happens to, okay, so what happens to renormalizations? Do we have to worry about this? And the answer, of course, will be yes. So we have renormalized the galaxy density field before, which is very nice, but we haven't renormalized the velocity field. And also here, what you can see is that there appear combinations of the products of the velocity field at the same position, right? Because here everything happens in real space, right? So we have a product of two fields at the same point, which typically we know in any perturbation theory and effective field theory is UV divergent, right? So we need to renormalize these terms for the theory to make sense. And well, physically, partly this also has to do with the fact that was mentioned earlier that if you just go on with the fluid equations, there will be at some point a shell crossing, right? So the trajectories will cross, and there will be points where the velocity field cannot be defined. So it doesn't really, so it's not even clear what we're talking about when we write down the Ricci space mapping, right? If the velocity field is not defined. So one way to deal with that is to, precisely kind of to integrate out the regions where the shell crossing happens, and then we're going to end up with the expression that manifestly has, well-defined velocity field. All right. So let's discuss this. Renormalization of local operators. Well, I should say that in the EFT in general, in the literature, there is a lot of discussion about the coarse graining and smoothing. So we discussed this a little bit in the context of the mass variance that diverges, and we need to coarse grain it. But for most of the other ingredients, we successfully avoided talking about smoothing. This is because there is a way to formulate things without explicitly ever using smoothing. So that is not the case for RSD. So here, again, we have to kind of go back to this concept. And the simplest conceptual way to do so is to say that our galaxy, okay, so let's start with the galaxy density field. And we'll see how the smoothing concept actually applies to the galaxy density field. And once we have it, now we'll be able to kind of go through all these other calculations easily. So the idea is when we write down our galaxy density field, it depends on the dark matter field that we square and that we cube, etc. So it's also UV dependent, right? It's also very UV dependent. So the way to deal with this UV dependence is to formally split this galaxy density field into the long wavelength part and a small wavelength part. So we can use some sort of low pass filter to define this, and the rest of the field will be the small scale galaxy density. So the idea then is that the large scale galaxy density field is your actual dynamical degree of freedom that lives in perturbation theory, and a small scale density field you are going to renormalize. And in in the quantum field theory context, this basically means that we're going to integrate out these modes, and this integration out will generate some effective operators that will renormalize delta G. So this is something that, well, for instance, you can read in the Peskin book on the renormalization of local operators. Now, in the context of the galaxy bias, this renormalization story works out very simply. So again, the idea is that now we take this expression and we integrate out the small scale modes, or in other words, we're averaging them out. So in QFT, normally you do so by writing down the path integral and writing down things like the one loop effective action. Well, here, let's say for simplicity, we're going to just take this expression and average out small scale modes over some ensemble with their distribution, right? So it will give us the exact same answer, and basically this is what the path integral does. Maybe a more physical way to think about this is that, well, what specifically will be important in the context of the Redshift space distortions is the Born-Oppenheimer approximation in quantum mechanics, where we have some small scale, well, we have some fast motion of the electron and slow motion of the nuclei, and we're averaging over the fast motions of the electron to get the effective field theory for the motion of the nuclei. So here we're doing exactly the same. Okay. So now, by definition, if you ensemble average the long wavelength field over the small scale fluctuations, this doesn't do anything, right? Because this doesn't have any small scale fluctuations. But then we'll have this. We'll have the averaged small scale density, and this one typically we renormalize with the counter terms, right? And the result of this will be the renormalized galaxy density field. And so this part, the long wavelength part, is easy. This is our usual part, but with the cutoff. And for this part, we don't really know what it is. So we need to, again, use our standard story of dimensional analysis and symmetries to write down all possible terms that this correlator that is averaging can depend on. And you will see again that just based on symmetries and dimensional analysis, the only thing you can write down is going to be the long wavelength density field itself. So let me write down delta 1L, like the filter, the coarse grain linear density field, and then the coarse grain quadratic field, etc. Because those are the only operators. And these are the operators that you already have here, right? So that's why in the context of the galaxy bias, this procedure basically doesn't generate anything new. It will just produce some unobservable renormalization of the original, let's say, bare bias coefficients that you have here. And in particular, well, something that we just discussed with Diego, you can define the renormalized cubic operator delta 3 that will look like this. So basically, you just keep this part for the renormalized delta cubed, and you select B1 prime such that it cancels the UV divergence, and you will see that this is the counter term that you need to select in this case. So this is delta 3 renormalized. Okay. Now, what does this all mean for the Redshift space distortions? Okay, so we have this term, which is kind of the first problematic term that we need to deal with. So let's average this term over the small scale motions. So again, in the context of Redshift space distortions, really the kind of physical picture is very simple in some sense that you have this small scale virialized motions. Now this motion, is very fast, and the modes that undergo these motions, these modes have decoupled from our perturbation theory. So these are non-perturbative modes. They're fast. They're contained here. So want to average over them just like one does in the Born-Oppenheimer approximation. Okay. Yeah, there is a bracket. We will recover this bracket in a second. At the moment, let me just focus on this real space expression. Okay. Okay. So then, okay, let's see. So we apply this. We apply this expansion. So what we're going to get is that we'll get 1 plus delta galaxy long u long, Okay, so this is the part that just involves the long wavelength fields. Then we'll have the renormalized short scale part of the density field and the long wavelength velocity. Then we'll get a part that will look like this. All right, so it makes sense to consider this combination because in principle, well, we know what delta galaxy long is, but we don't know what this guy is, right? And we have known function times unknown function, we're going to have an unknown function. So it makes sense kind of to absorb it here just to simplify notation. And from this expression, you can see that this part is delta galaxy counter term, right? Is what we can now combine with this term to get delta galaxy renormalized times u long. And this is something that we can just write down this correlator, the average over the small scale motions. I'm just going to call it OU. Okay, so this is a new local operator that appears here. And we're going to use, well, it has one SO3 index. We're going to use now symmetries and dimensional analysis to write down the most general expression for this guy in terms of the long wavelength fields. So this part, however, is completely fixed. So we know we have already renormalized the galaxy density field is a long wavelength velocity field, so everything is good here. All right, let's see. Let's see what happens now at higher orders. I mean, you can kind of already guess what this operator could be. Again, based on symmetries and dimensional analysis, it has only one index. So it should have a gradient. And then the only field you can write down is the density field. And maybe one important point that I would like to make here is that this could not be, so this needs to be a scalar under Galilean transformations because this already has the proper Galilean transformation properties, right? So if you want to preserve Galilean invariance, this needs to be the scalar. So this guy cannot depend on the velocity field, right? This will break the Galilean symmetry. So that's the only functional form you can write down when you kind of use the EFT arguments to express this, all right? Okay, but now I think that the kind of picture, the machinery of this is very clear, right? So we first write down something. We write down our correlators in position space. We split them into the long wavelength fields and the small short wavelength fields, and then we integrate out the small scale mode. So we average over the small scale motions. So in particular for this correlator, what we're going to get by using the exact same arguments is going to be, well, first of all, a similar part that involves the renormalized galaxy density field and the velocity field, the long wavelength part of it. So this part is very nice. So for this part, we can just use these kernels right away. And then there will be additional contributions. And if we just, again, go through all the math. So let's see. So first of all, we're going to find this correlator again times u long. And we already have an expression for it, right? We know that it's OUI. So we're going to obtain the exact same correlator that we had before. And then by symmetry, we'll obtain, well, a correlator of a different index. And then there will be a term that involves only the small scale modes of both the velocity fields. So this will be a new counter term. Okay, and we can continue this with the other field as well. But this is fine. At the one loop order, just by power counting, we're not going to get any new counter terms from this expression. So it will only generate terms that are relevant beyond the one loop power spectrum. So this correlator actually, even though we can totally go through the renormalization and write down similar operators is not going to matter. So I'm going to ignore this term. Okay. Are there any questions? Okay, if not, let's write down now the symmetry-based expressions for these operators. So we have one operator, which is this. So I've already argued that the only thing you can write down is going to be this, plus higher orders. Now for this other operator, Oj, oops, u squared. So again, this operator needs to be a scalar under Galilean transformations. So it cannot depend on the velocity field. It can only depend on the gradients of the velocity field, but at lowest order, the gradient of the velocity field is a density field. So we're only going to have the density fields here and the tidal fields. So there are only two, at the lowest order, there are only two tensors that you can write down here. You can write down the Kronecker delta times the matter density field, and the other thing you can write down is the tidal tensor. Again, I recall that phi hat is the gravitational potential renormalized, well, normalized such a way that its Laplacian gives you the density field right away. So these are the only terms that you can write down that are based on symmetries. And now you can compute the renormalization of these local operators that appear in this expression. So compute renormalized products. So for the first one, so I'm going to write this down very explicitly. So we have 1 plus delta galaxy, UE, then ensemble average, and then we need to take the Fourier transform of this. So first of all, it will generate a term that will look like this. That just will involve the usual long wavelength velocity field and the renormalized density field. So this is this term. And then the contribution from the operator OIU from here will be very easy to compute. So we have 1 kz here and 1 kz from zi times di delta. So we're going to get 2 kz's, so kz squared times delta. And in linear theory, we're going to evaluate all these things at lowest order, so it's enough to just replace delta with delta linear. Okay. So likewise, for the second term, we can also write this down easily. So there will be a term. Okay. Let's do this. There will be a term that already has only the renormalized and long wavelength fields. That will basically be, the exact same expression. But now here you'll have 1 plus delta galaxy, same coefficient, ULI, ULJ. And then you'll have two counter terms. And because of this kz squared, they will be multiplied by kz squared. C2 delta minus C3 times mu squared times delta. Okay, let's do delta 1. All right. So altogether, as a result of this renormalization, we're going to get the final expression, delta in the redshift space for galaxies is delta galaxies redshift space in standard perturbation theory. Okay, standard perturbation theory in this context means that we are evaluating we are taking these kernels and evaluating the velocity field in standard perturbation theory without worrying about renormalization or things like that, right? So we'll have this usual expression given by these kernels, and we'll have the counter terms that will take a particularly simple form. So you can see in terms of the functional dependence that, so it has the kz squared, which is k squared times mu squared. And then these two terms are degenerate at the level of the one loop galaxy power spectrum. So you can combine them into C1 tilde. And then you have this other term plus 1/2 C3 f squared mu squared. So this term is well, not degenerate. It has an extra mu dependence that the other terms do not have. But this will be your full result. So you will see that at the level of the one loop galaxy power spectrum in redshift space, there will be altogether two new deterministic counter terms. And you can see the power of dimensional analysis and symmetries here again, because you can see that the mu dependence is fixed. So you have only k squared mu squared and k squared mu to the 4. For instance, you don't get k squared mu to the 6 or k squared mu to the 8 or any other combination, right? Which is a non-trivial fact, because if you compute these SPT loop diagrams, you know, P22, P13, you take the UV limit, you will find some terms in the UV limit that will look like k squared times mu to the 6. But this will be renormalized by this coefficient times the Kaiser factor. So it's a non-trivial statement that you only need two coefficients to renormalize all of UV divergences in the one loop power spectrum that come from the deterministic diagrams. So I make this comment about the deterministic diagrams because there are also the stochastic contributions here. So basically in these expressions that we wrote above, we wrote down only the possible combinations that involve the density fields. And in principle, at higher orders, you need to write down the velocity fields, etc. But as we know from the discussion of the bias tracers, also there could be some stochastic components. And the stochastic components, so before we only considered the scalar stochastic field epsilon, but in the context of redshift space distortions, okay, stochastic components. You will see that in principle, this term could depend. So let me write down this. So the right-hand side of this expression could involve some field that I'm going to call epsilon I, right? So this will be a stochastic vector field, right? You can think about this as a, well, basically small-scale velocity field of galaxies inside the halo. And this field has completely decorrelated from the cosmological initial conditions, so it only correlates with other stochastic fields. So likewise, for this term, again, we can write down something like this, plus also some other field, epsilon times delta ij. So it turns out that this combination, in fact, will be, so this term will be degenerate with this one, so we can ignore it. At the lowest order, at the one loop order in perturbation theory, we can ignore this term. So you will see that there will be two extra stochastic fields that appear, sorry, ij, that appear as a result of renormalization. And this field will correlate with the galaxy stochastic field, right? We also have the galaxy stochastic field, don't forget about that. And again, if we want to write down their correlators, the only guide we can use will be symmetries and dimensional analysis. So in the EFT, we know that at lowest order, this stochastic vector field will correlate with itself to the Kronecker delta times some constant. I'm going to call B1. Now, it could also correlate with the galaxy stochasticity field, but then the result will have to depend on the vector ki, right? Because this has one index. The only index we can have on the right-hand side is going to be the index attached to ki times B2. And then the epsilon field, the spin 2 field, will be correlating with the galaxy stochasticity field, again to the Kronecker delta. And in principle, you can write down more complicated correlators. You can correlate this guy with this guy, etc. But at the level of the one loop perturbation theory, these are the only three correlators that we need to keep track of. So now we can compute delta stochastic, okay, in redshift space, delta, okay, let me write this down like this. So now we can compute, from this expression, we can compute what is going to be the contribution to the total galaxy power spectrum from the stochastic effects. Maybe, yeah, to make this discussion, okay, to make this discussion a little easier, let me summarize what we have so far for the stochastic effects. So we have the galaxy, we have the vector field, we have the spin 2 field. Now, if I recover all the appropriate factors of f and kz from my redshift space mapping, I'm going to find the following expression. So you see that the stochastic vector field will be coupled to a line of sight, and then the spin 2 field will be again coupled to two lines of sight. Zi, Zj. To recover hat. Okay. So here basically I'm just squaring this expression. So in one loop perturbation theory, I want to keep track of the terms that scale up to k squared, right? So I wanted to include terms that have scaling k to the naught and k squared. And just from this expression, okay, so I'm going to find first my usual galaxy stochasticity field. Then on top of that, there will be the correlation between the stochastic vector field and epsilon galaxy, kz, zi. So I'm going to write this down very, okay, I'm going to write this down schematically, ignoring some of these coefficients, 1/2, f, I. So there will be this correlator. Then on top of that, there will be a correlator between the spin 2 field, epsilon galaxy, zi, zj, kz squared. And then there will be the correlator that involves two stochastic vector fields. And now from these expressions, we can totally use, these correlators that I wrote above, and you will see that. So for instance, this will have extra ki that when we contract with z hat is going to produce kz. So altogether, this will scale like kz squared. This other contribution, so it has delta ij. So since z is a line of sight unit vector, delta ij times zi zj will be 1, right? So then we'll be left with kz squared again. And then finally, this term, again, epsilon I and epsilon I, they correlate to delta ij. Delta ij times zi zj is 1. So this is kz squared again. So we will see that altogether we're going to end up with the usual galaxy stochasticity power spectrum plus something I'm going to call alpha tilde 2 that only depends on kz squared. Or in other words, well, now I can restore my dimensional parameters. I know that the galaxy stochasticity depends on the 1 over n bar. So I have my usual Poisson stochasticity, k-square correction. And then on top of that, I will have the kz correction that I'm going to rewrite as k-square mu squared. And if you want, in principle, we can introduce k nonlinear squared here, such that coefficients alpha 1 and alpha 2 are dimensionless. This is another powerful result of the EFT. So you can see again that from symmetries and dimensional analysis, the only stochasticity correction that is possible will be k squared mu squared, right? For instance, there will be no term. So there will be no term that would scale like k to the naught times mu squared, right? So on very large scales, the stochasticity, the error power spectrum, the short noise power spectrum is always white. And then the mu dependence enter first time is k squared mu squared. Maybe I can show you. No, it's not gonna. Okay. In here. Well, there is no mu to the 4 here. Well, yeah, I would say, look, symmetries and dimensional analysis, this is the only tensor structure you could have. So my like the simplest EFT kind of explanation is that at lowest orders, you have a finite amount of structures available to build your effective operators. That's why you always end up with very simple power laws. So it's impossible to have higher order of mu, because higher order of mu also in the ratio space mapping, it means that you will need to go to really high orders, right? Because every order has, first order has mu squared, mu to the 4, etc. So in other words, this is the argument that you can also use. That the ratio space expansion is also expansion in mu, kind of automatically. Okay, so yes. Oh, right, because, so you mean this? Right, because this correlator, as we wrote down, is proportional to ki. So ki, and then you have kz here, right? So ki zi times kz altogether. This is just projection of k onto z, which is kz, right? Okay, excellent. Sure. Okay, so I prepared here a couple of slides just to illustrate the material a little better. So this is the slide that shows the ratio space multiples that we introduced before, and like the general physical understanding of the multiples is that the monopole basically gives you the auto spectrum of the density field. The quadrupole is the cross spectrum between the density and velocity fields, and the hexadecapole is the auto spectrum of the velocity field, very roughly. So, and that's why, each one of them is going to be suppressed by f. So the velocity is suppressed by f, as we discussed. F is 0.5 at redshift 0, and the density field gets additionally boosted by the galaxy bias. So that's why there is a kind of an hierarchy between these correlators. Now, this hierarchy is not true in general for any tracer. For instance, for the Lyman alpha 4s, the situation is different. The quadrupole is enhanced compared to the monopole. But for galaxies, this is always the case that the bias is greater than 1, what the galaxy we observe, and the f is less than 1. Now, all these EFT expressions that I wrote before, so including specifically the expressions for the density field, such as, for instance, this one, right? Okay, let's say for galaxies, we had this expression that has different operators, and then we can also compute an analogous expression that involves kind of all the higher order operators that depend on mu in ratio space. So you can evaluate these expressions directly at the field level and compare with the simulations. So you can, in other words, you can have a simulated universe with some given initial conditions that you know, and you can forward evolve. So you can take these initial conditions and evaluate the EFT fields for them and compare with the full simulation. Well, in this particular case, I'm comparing against the HUD simulation, and you can see that the EFT results, they on large scale, they match, well, basically perfectly the full simulation result. That tells you that not only the EFT predicts well the correlation functions, it also predicts well the entire density field. And here the bottom panel represents Rescher space results, and if you look long enough, you will start seeing fingers of God and a Kaiser effect. So you will see, for instance, this cluster over here in real space gets more contrast, gets more nonlinear structure in Rescher space. So this precisely corresponds to the fingers of God, and also its extent becomes a little bigger, so it gets more fluffy because of the fingers of God. So all these effects are very real. And then you can compute the difference between the EFT field, so delta EFT, deterministic prediction minus delta simulation. So you can compute this, and kind of by construction, this will be something that precisely evaluates the stochastic component, right? So you can check how the stochastic component looks like in actual simulation, and you see that indeed it precisely matches the EFT prediction. So the error power spectrum, the stochastic power spectrum is constant. So it's wide on very large scales, and then the scale dependence begins as k squared. So here I'm showing you results for the HUD galaxies and also for the galaxies from the Millennium hydrodynamical simulation. You see that, well, something interesting that you would see is that the scale dependence in real space, so the scale dependence due to this guy, turns out to be very small, which is a good news. So this coefficient in some sense turns out to be small for actual galaxies from those simulations. But in a redshift space, it becomes bigger, and the mu dependence of the error power spectrum is precisely capturing by k squared mu squared on very, very large scales. Now, one point that I would like to make here is that you can also notice that the scaling of the error power spectrum of k squared mu squared, so this scaling is nice and valid on large scales, but as you move to scales that are relevant for the galaxy surveys, like the BO scale around 0.2, you see that the scaling becomes more shallow, right? So that means that, okay, you would need to keep include in principle more higher order terms in the EFT, but since it's getting more shallow, it means that the function that you have here is more slow, right? So it doesn't really behave like a Taylor expansion anymore. So you need to kind of resum it in some sense, right? So in other words, the Taylor expansion doesn't represent a good approximation of the smooth function. That kind of raises some concerns about the applicability of the EFT at very small scales. Maybe in the literature you've heard that, well, you've seen that there are some discussions about the possibility to resum the deterministic part, but the point of the deterministic part is that it only captures this, right? It doesn't capture, in other words, it doesn't capture the error power spectrum. So you can resum a lot of diagrams that are sitting here, but it's not going to improve your error power spectrum because it's a separate expansion, right? So in other words, these resummations, while they can, improve the K reach a little bit, they're not going to fix this problem of the scaling. And that also tells you that if if you're concerned about the validity of the EFT, what sets the limits of the EFT is precisely the stochastic part, because the stochastic part is unrelated to the cosmological initial conditions. So everything that appears here is some extra nuisance, right? So this is like a true nuisance that is not related to any BSM physics or initial conditions and stuff like that. So every single time that you need to write down more complicated function to capture it, means that your cosmological constraints are going to suffer. And you can see that the exact kind of scaling of the error power spectrum with K is also different in the HUD galaxy context and the hydrodynamical context. So in other words, we don't really have any good understanding of how this, how the error power spectrum should behave beyond this limit. So this represents the kind of limiting point of the effective field theory in retro space. All right. Are there any questions? Yes, please. Oh, yeah, this is an excellent question. So you're asking, so we had this dark matter epsilon, right? And we had the galaxy epsilon, right? Right. So they should also correlate, right? And one observable where they would correlate is the galaxy matter cross spectrum that, for instance, you could measure by means of the cross-correlating galaxies and SIMBI lensing, because SIMBI lensing probes really, as Julien described, probes the matter field. So in that case, you have to compute this, and you know that the dark matter field, it scales like k squared times epsilon from the stress tensor, right? Epsilon tau. So now, and this scales like constant, right? So this will start, so epsilon tau, epsilon galaxy. Again, this will be constant plus k squared, k to the 4, but now you have an overall k squared from the Peebles argument. So this will start as a k squared. Okay. So the stochasticity, and that's why this is kind of standard story why we like cross correlations, because cross correlations, they reduce stochasticity, they reduce the shot noise. Oh, I mean, in the galaxy power spectrum, you have the galaxy field, right? I mean, you have delta galaxy, right? I mean, normally, okay. So you're saying we have, for instance, B1 times delta matter, and delta matter has stochasticity in it. Yeah, sure. You could include this, and then, since it produces a k squared, the only thing it will do, this correlator, it will lead to an unobservable renormalization of the alpha 1. Yes, exactly. So you could include this, but it will not do anything. Okay, so it will be totally degenerate. All right, are there any other questions? Yes, Cooper. Yeah. Yeah, this is an excellent question. So this idea, the simplicity principle of the EFT, you can apply to other observables as well, which will mean that for any field you're looking at on very large scales, it will trace the underlying matter field in a form similar to the bias expansion, right? The only difference that for different tracers, there will be different symmetries that you need to worry about. For instance, for the Lyman alpha forest, you will have, instead of the rotational, full three-dimensional rotational symmetry, you will have only rotations around the line of sight, because Lyman alpha forest kind of fundamentally lives on the line of sight, right? So you will have less symmetries. Less symmetries means you'll have more EFT operators. In the context of lensing, for instance, an important effect is intrinsic alignment, which is the kind of extra correlation of the galaxy shapes with the tidal field, which is a spin 2 observable. So now you would want to write down like the galaxy bias expansion, but for a spin 2 field. And that's why the tensorial dependency will be slightly different. And all these stories that, they will also have the stochastic contributions. You'll have to apply some sort of dimension analysis and Taylor expansion. All these stories will work out exactly the same for all these different tracers. I feel like I'm running out of time. Or you had a question? Um, I think this is fine. I was going to discuss some other things like the bispectrum, but okay, we can discuss this. This is too much. Bispectrum is too much. Okay, so I'll stop with this. Thank you. Sure. Yeah. Yeah. Yeah, there will be absolutely no effect on the transverse direction. Anything okay, anything. Well, for instance, here in this case, you see that this cluster on the upper left side is kind of fluffy, but it's fluffy for every single line of sight, right? It's not because something's happening in orthogonal direction. No, it's every line of sight gets like fluffy. So that's why the whole cluster becomes fluffy. Yeah, sure. Yeah.
There was a lot of reasons that we did a lot of lower work because we don't care about the Euler picture don't care about the motion of the fluid parcel.
Yeah.
Like when we look at density, like for example, like the non-locality thing.
Yeah.
Like if all of those are all of those still there if we just do Lagrange perturbation theory?
No, if you do Lagrangian perturbation theory automatically implements this story that your final result depends on the flow evolution. So in some sense, it's a more physical approach to do the calculations, but also the calculations become slightly more complicated. So the general statement is that if you naively interpret, take the galaxy bias as an expansion in terms of the nonlinear matter field, you can compare it to the field level, and you're going to get terrible maps, right? The linear bias expansion, the Eulerian bias expansion works terribly at the field level. However, if you Taylor expand it, if you any nonlinear matter field you expand as delta 1 plus delta 2, etc., you are going to get expressions that are equivalent to the Lagrangian ones. So the statement is that in perturbation, and now if you do that, it will work, and the map level will work, everything will work nicely. So in perturbation theory, both Eulerian and Lagrangian pictures, they'll give you the same answer. So that's why in my lectures, I focus on the Eulerian picture just because the calculations are a little bit simpler, but it's true that a lot of the stuff that I was talking about, IR summation, the flow evolution, they are automatically implemented in Lagrangian perturbation theory. So in some sense, more superior.
So can I say that there's also always this question is if I just sum up all the loops and all the things,
yeah, yeah.
Non-preservative thing, are both when I do completely the entire non-preservative picture, is they separate with the non-preservative picture?
So the statement is that in the EFT you can resum a lot of diagrams, and you are not going to capture any non-perturbative effects. You will only capture, as you can see in these plots, you will only capture the correlations on large scales. And when you move to small scales, you will start finding big error power spectrum that will kind of dominate the signal. So it doesn't matter how many diagrams you resum, your EFT converges only as long as k is less than k nonlinear, right? And beyond k nonlinear, even if you could resum infinitely many diagrams, it will not help you. Yeah, that's right. There was a very nice paper about this by Matt McQueen and Martin White about perturbation theory in 1+1 dimension. In 1+1 dimension, you can resum exactly the entire standard perturbation theory, and it doesn't converge to the right answer. You can take the Lagrangian perturbation theory, which again is exact already in the Zeldovich approximation, and also doesn't describe the right answer, right? So all these resummations do not work, and in 1+1 dimension, you can see this very clearly. Okay. Yes, please. That's right, yeah. So I'm minimizing, okay. So I'm minimizing this difference, and I'm finding the EFT parameters that minimize this, right? So the error power spectrum, so in some sense, this is the best case scenario. Well, right, this is the best case scenario because this minimization will automatically give you the most optimal density field and the smallest possible noise, right? And this is the limit after you have optimized everything, this is the noise that you get. So it's still kind of significant. Right? Yeah. Yeah. Oh, yeah, this is an amazing question. So we, in cosmology, as you know, we measure information in terms of Fourier modes, and we know that current surveys such as DAISY and Euclid, they will basically see as many modes as Planck, or maybe a little bit more modes. But with future surveys such as MegaMapper or SPEC-S5, we can get orders of magnitude more modes, right? And if you talk about 21 centimeter, we get many orders of magnitude modes. So in terms of large scale structure, this kind of reservoir of modes is pretty much untapped. Okay. Now, how to convert these modes into actual cosmological parameters, this is another story, right? But